Today we are going to be talking about one of the most fundamental elements of crypto, or primitive of crypto, which is privacy. And we'll specifically be talking about zero-knowledge proofs, which is ZK. And a little bit about myself. I'm mostly a software engineer. I just started doing cryptography, and I'm a founder of Kage, or Kage Protocol. We basically help institutions invest and trade crypto assets privately. And I also work with Project Takeon at zkApps. Are you guys familiar with zkApps? Yeah, great. So I also help with scaling zkApps. We're working on something called Project Takeon, and it's meant to improve scalability of the zkApps architecture. And prior to that, I've also worked at previous protocols that are focused on ZK and implementing programmable ZK applications. So today we're going to be talking about ZK and the future of privacy. And I'll try as much as possible to reduce the complexities so we can all get along easy. So before I go very deep into the complex part of explaining ZK, Eric Hughes is one of the founders of Cypherpunk, and he made a statement about 30 years ago. He said privacy is necessary for an open city in the electronic age. And this was way before blockchains existed. This was when things were mostly text, emails, and Web 1.0. And I think one of the most important word in a statement is he used the word necessary, not optional, because privacy is basically our sovereignty. It's very fundamental to who we are as human beings. And Ethereum basically builds one of the most fundamental applications that we use today. I mean, in terms of blockchains. And because it's a public ledger, this basically led to what I call the transparency trap. And so we live in a world where every payment, every trade, every mistake, literally every relationship you have, it's on the public ledger, and it's literally recorded forever, and anyone anywhere can literally access them via Etherscan or any scanning tools. And bringing it back to what the cypherpunks were basically fighting for, building towards for the future of the internet, they basically never asked for perfect transparency. It was more about selective disclosures. If I use any term you guys don't understand here, just holler at me. I would explain. Okay, and so zero-knowledge proofs are a way of escaping this trap. Just to put it in context, if your entire life is basically public, it means people would be able to access all your personal information publicly. People would be able to know that you guys are literally here today publicly. You guys paid for a beer at the bar just because you use USDC, and it's available publicly. So this is what ZK basically helps you with. And so moving into the topic of today, what the F is, what the F is ZK. So ZK basically proves truth without actually revealing the evidence. It's basically lets you show correctness without showing the data. It helps you prove a fact while keeping the fact hidden. Okay, so it helps you reveal the result of something, but not the input that you actually made. It's basically proof without disclosure. And So to prove the validity of a statement, so this is me trying to explain the underlying factors that make ZK what it is. I would still go further along as we progress. So to prove the validity of a statement without revealing the statement itself, there are mostly two parties involved that makes ZK work. One of them is the prover. The next one is the verifier. And in some instances, we have third parties, which are called the issuer. So how does this work together? The prover is the person trying to prove something. The verifier is the person trying to validate that whatever the prover is proving is actually factual or real. And the verifier could be somebody who actually issues the the issuer could be somebody who actually issues the particular information that needs to be verified or proven. And it could be the government, it could be anybody, literally. And yeah. So I'll give you guys a real life explanation of ZK in the real world, so you guys could, really understand what we're talking about in terms of provers, in terms of verifiers, and in terms of issuers. So what exactly does ZK do, and how does ZK work? So ZK could enable you prove that you weigh less than 100 kg without actually, making people know that you're actually 99.9 kg. Basically, you weigh less than 100 kg. So, for example, if you get a report from the health facility that this is your weight, you want to prove it to be able to fly or do something, and you don't want to show your actual weight. You just want to show, I'm lighter than 100 kg. You could prove it with ZK. You could prove you're old enough to drink. You're 18 and 1 month old. You could prove you paid your taxes without actually revealing your income based on the threshold. You could prove you literally attended this talk, just like we use Pope. You could prove you're rich, you could prove you're poor, you could prove you're over 18, you could prove your credit score is above the threshold, which I explained, and you could prove you're 6 feet and not 5'10", the Tinder conspiracies, and so much more. So a live implementation of ZK is the Google Wallet. If anyone here is based in the US, you can basically upload your driver's license or your passport to the Google Wallet. And if you're trying to get a pass at something, maybe you go to a bar and they want to confirm if you're 18 years, but you just want to show you're above 18. You don't want to show your date of birth. You don't want to show your country of origin. You don't want to show all of those information. You just want to prove you're 18 years. So since you've uploaded your ID to Google Wallet, Google Wallet communicates with the issuer, which is the government that gave you the ID, to be able to verify those informations. And once you just tap to the bar or the club you go to, some of them have devices, some of them just need to see a proof that you're eligible to drink or something like that. You could literally just pop up your Google Wallet and say, yes, I'm eligible to drink, and that shows a real world use case of using zero knowledge proofs. And so how is that possible? How does this work without just, how does provers work? How does verifier work? What are the underlying cryptography, underlying mathematics that enables this happen? Yeah, so basically, proofs comes in 2 categories. We have interactive proofs and non-interactive proofs. Interactive proofs are basically the ones that we use mostly in Web3. And I will explain why. So before I go there, I'll probably explain non-interactive proofs first. So this is, I want to use this as a case study. So just imagine that, there's a ring-shaped curve, and there's a gate inside the ring-shaped curve that basically requires a password for you to go through. And your friend, you're the prover, your friend is the verifier, and your friend wants to prove that he knows a particular information because he's the witness. He has to go through the gates. If he goes through A, he's going to have to go through the password verification, and he could tell you, I went through A or I went through B while he's inside the gate. And if he goes through B, he could go in and come out the same way. So what's the point of all of this nonsense? The point is basically interactive is basically the prover and the verifier having to communicate every time on the validity of a statement or the validity of an action, basically. And yeah, so okay, good. So like I said earlier, if you entered through side A, you need a password to get through side B. And if you entered through side B, you could just come out the same way without having to use the password. So, and this is a good example because it shows like, whether or not you're required to use the password while doing this challenge. And yeah, so this literally makes up some of the core fundamentals of ZK proofs. There's the witness, there's the challenge, which is the question, and then there's the response. And we also have the witness, which are witness, provers, verifier, and like challenges. So this is basically not very sustainable in terms of interactive proofs are not very sustainable in terms of blockchain applications. Why? Because they have a big limitations. They have a big limitation. Even after, because most times, even after the verifier is like, satisfied that yes, okay, my friend knows the password and, I believe is, he went through the tunnel. The communication is only between the prover and the verifier. Third party cannot verify that, this guy's actually know the information or have access to this information. And yeah, so that sums up the slide. And yeah, so moving into non-interactive proofs, like I explained before, there are interactive proofs, which I just give you an example of communications between the both of them, and non-interactive proofs, which are used in most ZK blockchain-related applications. There are two types of non-interactive proofs. The first one, which is very, very early and one of the first to be implemented, zkApps was actually the first to do a run-in application of zero-knowledge proofs. So it's called ZK Snacks, and then there's ZK Stacks. We'll talk about ZK Stacks later. ZK Snacks means zero-knowledge, succinct, non-interactive arguments of knowledge. And the ZK stands for zero knowledge, which means not having any information about something. Succinct is because they are small and they are quickly verifiable by the verifier. So you don't need to take so much process to actually verify a particular set of information. And non-interactive, which I think I've explained, it means there's only one round of communication between the prover and the verifier. You don't need to do the back and forth every time, just once. And arguments means it's theoretically, based on math, very, very extremely unlikely to be able to fool the system or be able to trick the system into like passing an information that's not correct. And I would explain why, this is. And of knowledge can be constructed without having access to the information. And I think, just to explain further, ZK Snacks, they use a cryptographic primitive called elliptic curves. Basically, it's a method of creating and verifying these proofs. And one thing about ZK Snacks is that during the initial setup phase, the prover and the verifier must literally agree to use a shared key. This is called CRS, which is Common Reference String. And anyone with the access to this key would be able to have details or have information on what was actually verified and what was actually proven. And basically, this is what makes ZK Snacks possible. Okay, yeah, so to break it a little bit further, ZK Snacks consist of three major functions: key generation, proof generation, and verification. So ZK Snacks really comes down to these three algorithms: the setup, which is the proving, and verifying. So everything else is scaffolding. So basically, at the setup, you create the keys at that point in time. I think I explained at first what the setup entails, basically the proof and the verifier keys. So this is where the system basically takes the circuits. I would explain this also. And the system, the statement that we actually want to prove, we could say, so when you see, okay, I think I've not, okay, yeah. So for the setup, we need CXW. W is the witness. YX is the public input of the information that you actually put. So you create a witness automatically. And then we have a proving key, which the prover would use to construct proof. So this is W, which means witness. X is the public input, and PK is the public key, private key, sorry. So if the prover, which contains both the public input and the witness, is incorrect, the PRF, which is what is generated, basically at the moment you prove, wouldn't be valid. So it could be true or false depending on. So this is why when I said theoretical, it's almost impossible to bypass or to fool ZK proofs, is because there's basically maths behind it. So, and yeah, so a proving key, which the prover will use to construct the proofs, which is the PRF, and a verification key, which is VK, and the PRF, which is the proven key, and then we have X, which is the public input. So a verification, the verification key is what you could use to verify that the proof was, made, and either the proof was valid or invalid. So basically, so at a very, very high level, ZK snacks are just you compile a proof, you prove it, and then you verify it. Compiling is where you set up the information, the public inputs, and the keys, and proving is the computation, where you generate the PRF, and then verifying is the verifying key, which you as a user will be able to verify a particular set of information. So just to take this back a little bit to our first example, so there's a correlation of thoughts or explanations. So when you want to verify that you're above 18 to be able to drink, someone or the developers basically set up the proving, done the setup of the provers, and so at the moment where you prove, the witness is your issuer, for example, like the government. They know that you proved, and the public input is the information that you uploaded, and then the private key is the one that you are the only person that's able to verify this particular set of information. And what the verifier just needs is the verifying key and the PRF, which is the proof that was. So whenever a proof is completed, it creates an hash function. Have you guys done a transaction before using Ethereum? So it has an hash function on ETH. So basically that hash function is on the verifier, and they could verify the hash function, which is the PRF that was generated when the verification took place. And X, your public input. And yeah, so I think one very, very important thing to note is both the prover and the verifiers, although explained in maths, they are all algorithms. They are not engineering, especially algorithms. Algebra. So yeah, talking about stacks, I'm more of a snack builder, so I'm not a stack builder. I think stacks could be better explained as the cousin of ZK snacks. They came very, very much later. Vitalik calls them the cousin of ZK snacks. So snacks means, or stacks rather means, zero knowledge, scalable, transparent arguments of knowledge. And why is this scalable? It's I explained that snacks were succinct, which means they, require small proofs. So rather than stacks being succinct, they are scalable, which means they could generate and verify proofs with larger witnesses. The previous explanation I gave to you was you only did probably just one witness to be able to attest that this particular set of information is accurate. So for stacks, you could use a host of witnesses, and yeah, and it does it way more efficiently than ZK snacks. And yeah, they're transparent. They're not basically private by nature, although you could build more cryptographic primitives that make them private. I think another very important thing is that there's no trusted setup. What I mean by trusted setup is, when I was talking about setup at the previous slide, I told you there was a generation place and the setup where you generate the PK and C and X keys. For stacks, there is no setup, so it's basically publicly verifiable randomness to be able to generate the shared key. And yeah, that's about snap story. I won't be going deeper. I'll probably publish a blog later on this in case you guys want to read. And yeah, so let's leave maths for a little bit and then we'll go back to it. So what are the use cases of ZK? Early on, like I said, Zcash used ZK for private transactions. Sorry, I didn't attach as much logos as I should. We have a lot of applications basically using ZK in production today. I was just very, very lazy, so start looking for their logos. So we have Zcash for private transactions. They also use snacks. We have Tornado Cash. I'm sure a lot of us are familiar with Tornado Cash. There's ZK Money. There's Hashtag. It's an Ethereum L2. We also use ZK. There's Maiden. There's a host. There's Intmax, like a host of ZK in production. And then we have ZK for scalability. So we have ZK for privacy, and then we have ZK for scalability. And basically, stacks are used a lot for scalable solutions. You know, upgrading the blockchains, being able to verify information faster with multiple witnesses and all of that. There's ZK Sync doesn't use stacks, by the way. They use snacks. Polygon EVM, I think they use snacks. And there's Cairo. Cairo is StackNet. You guys are familiar with StackNet? The Ethereum L2. Okay, great. So Haley will be disappointed, but yeah. So StackNet is a very, very famous Ethereum L2. They use zero-knowledge stacks to scale the blockchain. And yeah, for identity solutions, we have ZK passports, we have Barrymore ID, we have Google wallets, like I mentioned, and a lot of cases. So fortunately, unfortunately, we are only talking about privacy. So I'm not going to be talking about like other use cases of privacy of ZK outside of privacy-related solutions. But basically, outside of this, ZK could be used in healthcare, could be used in analytics, data, could be used in it's currently used by Adrill, the defense tech company. So yeah, it could be used in as many fields as possible. For health tech, you could imagine that you want to probably go to do a blood test, but you don't want them to know your origin or whatever. You just want to give them a particular set of information, and you want them to only see that information you're giving them. So blah, 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 blah. There's a lot of use cases for ZK, but primarily for privacy, private transactions. I could send you $1 and nobody else on net would know that we actually made a transaction. I could do it anywhere to anybody in the world. You could scale the blockchains with it, and I could prove, I could protect my identity with zero-knowledge proofs. So yeah. So yeah, let's talk about the beauty of the mathematics. I will try as much as possible to scale down some of the components that makes ZK possible. So I started with Sudoku because I think we are familiar with Sudoku, the game. Yeah, so basically I'm using Sudoku to represent circuits. Circuits are a fundamental in zero-knowledge proofs. They are constraint puzzles. So basically, if you're playing Sudoku, every box has to, and every column, they have to be, they must satisfy the rules of the game. You can't put a random number in a random box. So a ZK circuit works the same way. You have a secret solution, and the system checks whether all the constraints are satisfied without ever revealing the solution itself. So imagine if you have a Sudoku puzzle and there are numbers placed everywhere, and you could actually verify that those numbers are actually accurate or inaccurate, just based on ZK. So circuit works in a similar way. Yes, and the next one is elliptic curves. So elliptic curves are they're basically like the playground. So that's where you use structured algebraic addition and multiplication to behave in predictable ways, and predictable and verifiable ways. And then we have pairings. Pairings are like magical tunnels, basically between two mathematical spaces. So you could use pairings to compare. You could use them to create information across groups and compare information across them. And they're basically what makes ZK snacks succinct, and they help with like smaller proofs because you could do easy comparisons as they scale, and they also help with fast verifications. And so don't worry if you guys are not like really deep into cryptography. The important idea is that math is beautiful, and these structures basically, are basically what enables ZK prove that prove the truth of something without actually revealing information about itself. And yeah, when most people hear ZK feels like magic, this is basically because of algebraic circuits, peerings, elliptic curves. These are the fundamental primitives that basically makes ZK possible. And yeah, I have this actually. Okay, great. So yeah, we have always seen ZK is very, very powerful. It's a technology that doesn't rely on human errors. It relies on mathematics, which a lot of things that we basically use today, your devices has a lot of mathematics-based implementations. And yeah, but it also comes with its cons, basically because implementing ZK in production is very, very hard, and it's very, very messy. And I'll just go over some things that people don't like to talk about. This was supposed to be more of a dev conversation, but I'll try to break it down in a way that we could actually understand its limitations, and not just its limitations, but its limitations with the implications of tools or products that we use that use ZK cryptography. So yeah. Sorry, I use late problems, late ZK. I don't know what that means. It just sounded nice. So basically, so all the problems that happen that happens with ZK, they're not just random. They basically comes from all the primitives underneath it. The prover cost, basically when you're proving a particular set of information, it's very expensive because it relies on very, very heavy maths, amount of maths. And they're really not a flaw, it's just a consequences of mathematics. So ZK snacks also rely on like elliptic curves like I explained, MSMS, FSTs, very, very large circuits like the Sudoku I explained. And, so proofs are basically expensive to generate. And then there's a lot of bugs and constraint fragility. I would explain this. So what I mean by constraint fragility is that a lot of the circuits that I explained earlier again, they are very, very fragile. So if there's one piece of information or one piece of constraint that goes missing, and or one mistake in a polynomial commitment is broken, the whole system is basically like dead. So that's a very, very important thing, and you don't even see it because it just happens silently. So there are also metadata leaks because ZK doesn't cover it doesn't cover the network layer. It just encrypts particular set of information. I would go on to explain this further. And ZK basically only hides values of information. So whenever you make a transaction, it obviously hides the value, but then there are other things like the timing, the routing, what channel did the transaction used to take place, and who related the transaction. You guys know of routers like what good routers? Like Jupyter on Solana, Meteora, Uniswap. Yeah, so these are routers. So if you do a transaction between yourself or you try to do a trade, so ZK could hide your addresses, could hide the amount of your addresses, which are the values, but it might not if you don't create new encryption to be able to encrypt this information. Those things will still be available and you could get doxed. So, and yeah, I think I've explained circuit fragility. Basically, you don't, I think from a developer point of view, you don't just debug code as a developer, you basically debug algebra. So if you're not really good at math, it's very, very bad. And yeah, there's also the trusted setup risks. This is a very, very huge problem that a lot of people taking ZK to mainnet has faced. So at the moment of creating, proving, and verifying keys, if your setup is basically compromised, somebody can forge value looking proofs. and then get access to every information that gets transmitted over the blockchain. And user experience is horrible. But then some of these problems are actually getting fixed, by the way. ZK solutions and public currently being used at large. I personally worked at Mina protocol. We basically reduce the amount of maths developers have to do. So you just use your normal TypeScript. We created SDKs that you could use to build applications that rely on ZK without actually understanding the maths behind it. So we just abstract the maths away and you just have to do normal engineering. So what else? So yeah, all the problems with ZKs are just side effects of the same mathematics that makes it powerful. So a lot of us would not really care about those parts of ZK. We just want to use ZK related apps for the benefits that it gives to us. So this is why I had to implement this slide. It's the illusion of privacy. I mean, it's all an illusion. So and basically what I want to talk about here is there are a lot of wallets, there are a lot of applications that promise privacy, and they are actually truly not private because most ZK-based applications, they require something called a viewing key. And this viewing key is a special key that can decrypt all your transactions. So ZK alone, and because you need to be able to view your balance. So that's what the viewing key basically does for you. To be able to, you're on MetaMask, you want to see the amount of money you have. If it's a private MetaMask, you're going to need a viewing key to be able to decrypt the hash and be able to see your balance. So that's why viewing keys are essential in most ZK applications. So so the problem is most of these wallets, they use just ZK and they have access to everybody's viewing key or to all the transactions. So if they get sanctioned by the US government or by any government, they could literally just, give access to all your information in public because they can decrypt your transactions. So your favorite ZK wallet or your favorite privacy wallet might not be truly private. And some are like exchanges, custodians, compliance, sometimes even the RPC nodes or even the operators that have access to your viewing keys, depending on the architecture of the applications. And there are a lot, but I wouldn't be mentioning them. So DYOR. And so in these applications, we can see your transactions. Because of ZK setup, some people still deploy their ZK applications on AWS. And when you deploy there, they still get to be able to, decrypt your transactions. Some ZK applications have compliance partners to prevent the sanctions that happen to Tornado Cash, etc. So this compliance partners can literally encrypt your transactions. Some of them actually even leak the viewing key during, backup or when you're doing exporting of transactions. And some of them relay your transactions through centralized relayers. So if you see a privacy wallet that uses Uniswap or LeFi or Stargate or any of these routers, and you didn't see anywhere on their decks where they have something like, encrypted mempools or encrypted routers set up, it means there's a lot of possibilities for them to be able to decrypt your transactions. It means you're not fully like you thought you were. So some hardware wallets also store your viewing keys in plain text because they are not customized for private keys or customized for private wallets. Custodians of your wallet can also see it. Basically everybody can see it. So you just have to make sure you're using the right wallet. And why does this happen? I think I explained it before. It's the way ZK works. You need a viewing key to be able to do balance display. Some institutions must maintain auditability, so they need viewing keys to be able to do compliance, to prove that yes, we made $1 billion this year, and this is our transactions. People on the public can see it, but the tax agencies can see it if they have to. Also, some snack schemes are not designed for selective disclosures, and proofs basically only hide what the circuit hides. So this is a very, very fundamental part. And I think one way this has been getting fixed is something called client-side proving. So basically, you don't prove when you use a privacy app, for example, ZK passports, well, that's why I listed them there. If you use them, the proving doesn't happen on their servers. So there's no way they get to see the private keys. It actually happens on your device. So they found there are ways they were able to like reduce the amount of proving size so your phone can actually do proving, or your laptop or your devices can actually do proving. But this means it's a little bit large. For example, for an identity app, it's like 500 megabytes for just, scanning passport. Doesn't make sense. So yeah, that's just the cost of it. Also, be careful about compliance wrappers. A lot of mixers today, or a lot of pools today, or Tornado Cash duplicates, they actually have compliance. And this compliance actually have the viewing keys to be able to see your transactions. And yeah, I think that's about that. So one important metric to leave, ZK basically hides the values, the nodes, your balances, state transitions, and your addresses. It doesn't protect who relate to transactions. It doesn't hide timing correlation. It doesn't, decide who gets to see the viewing keys. It doesn't help you in any way with RPC leakage and, relay a user link. So this doesn't mean ZK is not useful. It just means it requires like other primitives to be able to make it actually sustainable. And some applications are actually using these other primitives, but some are not, or many are not basically. And yeah, so possible solutions, how do we solve this? On the computation part, you could combine ZK with MPCs. MPCs are multi-party computations, so it's basically instead of one witness to be able to do like computations, MPCs could connect multiple independent witnesses, or like, let's just call them validators, to be able to, it's a decentralized way of proving rather than just the operator being the witness. And yeah, so it means no single laptop can, compromise your privacy. There's also FHE. I personally love FHE a lot. It means fully homophobic encryption. And okay, so just imagine this. I have private data of everybody in this room automatically submitted to a form, but I use the private form, so I can't see your personal informations, but I want to run a computation or an algorithm, or I want to use Google Analytics on this particular form data. I could actually put this data on FHE and be able to actually do computation on this data blindly without actually seeing all your informations. So I could do an head count of how many people are here. I could ask the data for information about, where are people from here, what countries do they come from, and I could do all of those blindly without actually being able to see all of this information. So FHE is still very, very experimental. It has mostly been research papers until just a few years ago. So I don't personally trust it yet for production cases, but excuse me, a combination of ZK and FHE, it's a very, very good use case that basically, removes that part where somebody has to hold your viewing key, or an operator or the custodian has to hold your viewing keys. It could just be on an FHE basically. And then there's TEE. TEE means trusted execution environment, or something similar to that. So TEEs are not mathematics. TEEs are machines, they are devices. They're like servers, Intel SGX, etc. So they do private computations of information, and they are fast. But my personal problem with TEE is, again, this is a personal problem, is because it's dependent on hardware. And it means if you store your application's data on hardware, if a fire gets caught up or somebody targets that particular data center, it's really not as secure as zk itself. But yeah, it's fast. It's does basically everything it's meant to do, but it requires hardware, or it's dependent on hardware. And yeah. Okay, yeah. So I talked about the fact that ZK basically encrypts values and not the network or execution layer and all of those particular information. So there are other ways you could actually, the other primitives you could implement alongside ZK. So for Kage myself, my own startup, we basically use something called private intent. It means whenever you want to, let's say you want to do a trade, for example, you select Ethereum to USDC, you want to put a leverage of 20x, you want to use a cross margin of this amount, you want to do all of this. So these informations are passed to something we call solvers, encrypted. So there is literally no public channel of your messaging or the intent of what you want to do. And that's what we call private intent. So the way it currently works is there are cross-messaging protocols like across, like wormhole. When you want to do a transaction, they use intent. Intents are basically just, intent, like the English word intent. It means a request to do something. So the user experience might not feel like, you are passing a note. You might just be clicking buttons, but the backend understands it as an intent. So we use this intent privately, and then we have private mempools, which means even if we want to, we don't use any third-party routers, but even if we want to, we use them privately. So we could use a router through a shielded pool through our solvers to be able to do private transactions of any form that you want to do. And then there's also mixnets. Basically, it's mixnet rely on TEEs. They protect your IP through RPCs. They protect the timing, the routing information, and all of this information. And yeah, they're great. So the end game basically would be making sure you have encrypted states, encrypted execution, ZK verified correctness, and smart contracts where no one can see what's happening, but everyone can verify the result. So I think the live application of this, they're on testnet still, but is Aztec, the Ethereum L2, and I'm not posting any project. I've just personally built with Aztec, and they actually deliver on, they've been building for 8 years, so they actually deliver on all their privacy primitives, and that's probably the only thing I'll talk about. And yeah, good. Should I proceed? Okay, great. So yeah, personally, ignore my very nice fancy name. I personally think crypto is not crypto without privacy. I think privacy is a very fundamental value that makes crypto what it is today. It doesn't make sense that we exchange freedom and sovereignty for transparency. And yeah, privacy wafatsude means privacy is normal. So thank you, everyone.